This is very important, kind of important feature or note about homogeneous linear ODE. And I want to point out this works for homogeneous and linear ODEs. It says that if you get any solution for your homogeneous and linear ODE, multiply that solution by a constant, the new term is going to be a solution. Not even this. It says also this one, if you have two solutions and if you add those two solutions together, the sum is going to be again a solution. And this is what we call superposition principle or linearity principle. I'm going to just explain it in one example and this is the theorem. I'm going to call fundamental to remove the homogeneous linear ODE. And this is your second order, homogeneous and linear. You can see homogeneous and linear. I just highlighted one in red and one in blue. Now, if those two conditions are met, any linear combination of two solutions is again a solution. Now, linear combination, I'm gonna just show it to you, means if you take any solution multiplied by a constant, the new term is going to be a solution. If you take any two solutions and you add them together, the sum will be again a solution. I'm going to show you just one example. I'm going to leave you just with some details. Now, the first function, now I have this equation over here. It's a second order, homogeneous and linear. And you can see linear. And of course, over here, y prime is missing. And the coefficient of y prime is 0, and probably I mentioned before. Now, it happens to know that I know that the first solution for this equation is y1. I'm going to call it y1, it's cosine x. And the second solution, I'm going to call it y2, it's going to be sine x. Now, I'm going to show you later on how we find those two. But for now, assume that I gave you those two. Now, I want you to verify that this one is a solution. Now, to do this, we can see cosine x is defined. I have no problem over all real numbers. I can find the two derivatives, which is y prime and y double prime. And once you find those two different, substitute in your original ODE, and you see the second derivative plus the function itself, the sum is going to be 0. There we go. And you can do the same for the second one. It's very easy to verify and plug it in the given equation. Now, by this, I just showed that this one is a solution and this one is a solution. Again, as we mentioned before, should be defined, should be differentiable, and they should make your equation identity. And definitely those, you can see this one with this one going to make the identity, this one and this one is going to make it identity. So it's very clearly that those two are two solutions. Now, our theorem says if you take one of them, for example, cosine x, multiplied by any constant, think any constant, for example, a. I'm going to write y equal a times cosine x. Now, this new term is again going to be a solution for this ODE. Now, are we getting a new one? I'll talk about it in a minute. Now, not even this. If we take another constant, I'm going to call it b, multiplied by the second solution, again, this will be a solution. And this is going to be the first part of this theorem that if you take any constant and multiply by a solution, that will be again a solution. And I want you guys to verify those two things. Means you have to differentiate twice and plug in the equation. You will find out that this one is a solution and this one is also a solution. Now, before we continue, now, does y, this one, a cosine x, is different from cosine x? By the way, guys, they are not different. This is the idea, the concept over here, that those two, they are the same family. They are the same family. And this one is the same family as this one. So I'm not getting a new solution. I'm not getting a new solution. I'm just getting one of that family. So later on, You should keep in mind that we are talking about two families. This is one family and this is another family. Now, the linear combination of those two means the first solution with a constant, second solution with a constant, add them together. This again will be a solution. It's very clearly it's a solution because this one by itself is a solution. This one by itself is a solution. If you differentiate this one twice and substitute, you will figure it out. Please, guys, try to verify those three by differentiating each one twice and plug it in. You will find out that each one of those is a solution. And this is the concept of our theorem. And again, this theorem holds only for homogeneous and linear ODEs. Now, the last equation we call a linear combination of y1 and y2. Again, this was y1, this one was y2. So the linear combination is constant times y1 plus another constant times y2. Okay. Now, this equation was very clearly that it's homogeneous and linear. And those two solutions, so all conditions of this theorem met, so we can do it. Now, what about this? I gave you one y1, 1 plus cosine x, y2, 1 plus sine x. I am asking to verify that those are two solutions of the non-homogeneous ODE. Y del prime plus y equal 1. Now, to verify, each one is a solution. So differentiate this one twice. That's why we did this. Differentiate this one twice, plug it in. You're going to find out that you're going to be satisfied the equation. So y1 and y2 are solutions. Now, what about the sum? Means this one and this one. Sine x is cosine x, 1 plus 1 equal 2. Is this one a solution? Indeed, no, it's not a solution. I want you to double check. I want you to try this one at home. Why this one is not a solution? What's the difference? Why is this different from the first example? And this was the first solution. This was the second. If I added them, why is this one is not a solution? But I want to remind you about the two highlighted kind of things, homogeneous and linear. And if you look at this equation, it is a non-homogeneous. So the reason why this sum is not a solution because my given equation is a non-homogeneous. Now the same case for a non-linear ODE. When you go this a non-linear ODE. This one is a solution, you can try it. This one is a solution, you can verify it. The sum, which is x to the second plus 1, is not a solution and it is easy to verify. Differentiate this one twice, plug it in, you'll find out it is not a solution. Again, the theorem cannot be applied over here because my equation is non-linear.